Have you ever wondered how electric fields behave when there are many charges in play, all at once? It seems like a complicated dance of forces, doesn't it? But there's a beautifully simple principle that makes it all clear. Well, the principle of superposition for electric fields states that the total electric field at any given point in space is simply the vector sum of the electric fields produced by each individual charge, acting completely independent of all the other charges present. It allows us to break down complex interactions into manageable parts. This powerful principle holds true because electric fields are fundamentally linear phenomena, especially in a vacuum or in what we call linear, isotropic, and homogeneous media. Think of it this way: each electric charge, whether it is a positive proton or a negative electron, creates its own distinct electric field that extends outward into space. The crucial insight is that these individual fields do not interfere with or alter each other's existence or their respective strengths and directions. Instead, they simply coexist. Their effects combine in a straightforward, additive manner. This linearity is a direct consequence of the governing Maxwell's equations for electrostatics, which inherently possess this additive property. If you have two separate causes, like two charges, the total resulting effect, which is the net electric field, is precisely the sum of the effects from each cause acting alone. There are no cross-interactions, no hidden complexities modifying the individual fields before they combine. To successfully apply this principle, your first step is to accurately identify all the source charges that are contributing to the electric field you want to calculate. Once you have located these charges, for each individual charge, you will then meticulously calculate the electric field vector that it produces at your specific point of interest. This involves determining both the magnitude of the field, using Coulomb's law, and its precise direction, which points away from positive charges and towards negative charges. It is vital to remember to account for both aspects of each field vector. Finally, the last step is to perform a vector addition of all these individual electric field vectors. This summation will yield the net, or resultant, electric field at that particular point in space. What truly makes the principle of superposition so invaluable is its incredible versatility and broad applicability. It extends far beyond just simple point charges. This principle is absolutely crucial for understanding and calculating electric fields generated by continuous charge distributions, like charged lines, surfaces, or volumes, where you would typically employ calculus and integration techniques. Moreover, it applies directly not only to electric fields but also to electric forces, as force is simply charge times electric field, and to electric potentials. This makes it an absolute cornerstone for nearly all electrostatic calculations and advanced electromagnetic theory. It empowers us to analyze incredibly complex real-world scenarios by systematically breaking them down into simpler, solvable parts, transforming seemingly intractable problems into elegant solutions. Ultimately, a deep understanding of the principle of superposition fundamentally simplifies the analysis of intricate electrostatic systems. It empowers electrical engineers and physicists alike to accurately predict and quantify electric fields by systematically combining the independent contributions from multiple sources. This principle provides a clear, reliable, and foundational path to solving some of the most challenging problems in electromagnetics, making complex field configurations entirely comprehensible.